Welcome back. We just talked about binary numbers and how we can represent positive numbers between 0 and 2 to the n minus 1 with an n-bit binary number. Now obviously just the positive numbers is only one aspect of what you need to do in a modern computer. So you need to be able to do things like negative numbers and fractions and other things. So let's talk about negative numbers first. Okay. So how do we encode negative numbers? Again, we don't get a minus sign, right? This isn't like we're writing algebra on a piece of paper. There are only two things we can represent on a computer, 0 and 1. That's it. Everything has to be done with those two bits of information, okay? And so we can't just put a negative sign in front of something that doesn't exist. So we have to somehow figure out how to use series of zeros and ones to represent both positive and negative numbers and fractions and so on and so forth. Okay. Well, so here's one idea. We can just put a 0 in front of an n-bit binary number, and that represents a positive number, and a 1 represents a negative number. And I could have switched these, doesn't matter, just something. We come up with some standard, some language that you and I, or the computer and I, agree upon. Okay, so let's look at that and let's see what that would look like. So let's say I give you now a 3-bit signed binary number. And notice here I have to be very careful when I give you these binary numbers to tell you what it corresponds to. Because if I had just given you these, this could have been a 3-bit unsigned binary number. And this would have been the 2 to the 2 position, 2 to the 1 position, 2 to the 0. But I'm telling you now this is a 3-bit signed binary number. And so starting from the right, this is the 2 to the 0, 2 to the 1. But then this is the sign. 0 is positive, 1 is negative. And look, by the way, you notice here that, so all 4 of those are 0, and then the numbers go 0, 0, 0, 1, 1, 0, 1, 1. All of these are 1. Those are negative. Same thing, 0, 0, 0, 1, 1, 0, 1, 1. So you see you get the negative numbers here, the positive numbers here. Good. So if that's the sign, as we agree, and then I have a 2-bit binary number, well, we know what that is. This is 0, 1, 2, 3. Let's just make sure we understand that. This is 3 because it's 2 to the power 0 times 1 plus 2 to the power 1 times 1. So that's 2 plus 1 is 3. So same thing as we did in the previous lecture. Okay, so what about the 4 numbers below? Well, obviously these are negative numbers. 1, 1, 1, 1, 1. So what is the negative number? Well, it's whatever is in the 2-bit position. So that's 3, so this is negative 3. That's 2, that's negative 2, that's 1, that's negative 1. Well, this is a little odd. Now I have a negative 0, which of course is the same as 0. So that's a little bit of an odd thing with this representation. We essentially have two zeros, a positive and a negative 0. That's not great. There's actually other problems with using this type of leading bit for the sign, which I'm going to show you in a little bit. And this, in fact, is not what modern computers use. They do not use this. It seems like a really easy thing to do, and frankly, it's good for us as humans because I can look at that first bit, and as long as I know what it is, I can immediately tell you whether it's positive or negative, and then I just have to interpret all the bits beyond that. But as it's going to turn out for computers, it's a pretty clumsy representation. And instead of doing the signed representation, we're going to do what's called a 2's complement representation. So let me describe what I mean by that. So we need, again, a mechanism to represent positive and negative numbers. Okay? So I'm going to start with an unsigned, so that means that first bit has nothing to do with the sign right now. 4-bit binary number where the leftmost bit is always 0. Okay, so this bit is going to be the sign, but not in the way that I showed you before. Okay, so this number must be a 0 for it to be a positive number. Okay, and then this, of course, is 2 to the 2, 2 to the 1, 2 to the 0. So let's make sure we understand why that's 6. This is 2 to the 1, that's 2, 2 to the 2, that's 4, 4 plus 2 is equal to 6. Okay, good. And so we start with an unsigned 4-bit or 5-bit or 6-bit or whatever you want, where the leftmost bit is 0, and that 0, of course, is going to correspond to positive numbers, but again, not in the same ways above, and you're going to see in a minute why that is. Now, to make that number, to get negative 6, here's what I'm going to do. So we know how to do all the positive numbers, right? It's just 0 in the 4th position, and then you just run through all of the 2 to the 3 minus 1 possibilities for these 3 bits. Good. How do I make negative 6? So here's what you do. Take that representation of 6 and flip the bits. It's called complementing the bits. So 0 goes to 1, 1 goes to 0, 1 goes to 0, 0 goes to 1. That's the complement where every bit has been flipped. Notice that by definition, that first position must be a 1. Why? Well, because that is by definition a 0, and when I flip that, it's going to be a 1. So anything that has a 1 in that most significant position will be negative. But the interpretation is not the same as what I showed you up top, because that obviously is not 6 right there. That's something else. Okay, so we have to figure out what that actually means. Okay, so complement your binary number and then add 1. Okay, so here's my 6, 0 in the most significant position. Complement it. All the zeros go to 1. All the 1s go to 0. And then add 1. So what does it mean to add 1 to here? Well, 1 plus 1 is 2. That means I carry the 1, drop the 0. The 1 comes down right there, and I've got 1, 0, 1, 0. That is negative 6. Now, what's odd about this representation is if I look at just these 3 bits right here, that doesn't look like 6. 2 to the 0, 2 to the 1, that's a 2. So we can't look at this and just say, oh, the way we did with either positive numbers or with the non-2's complement sign thing. It's a slightly different representation, and it seems like we've taken a step backwards. This doesn't seem better. It seems worse. It seems more complicated. But it's going to turn out that this is not written for you and me. It's written for the computer. And I'm going to show you in a minute why this is a really nice representation of negative numbers for computers, even if for us it's a little bit harder to read. All right, so let's look at this now. Let's say I have a 3-bit signed using 2's complement binary number. All right, so let's do the easy ones. So the positive 0 through 3 is what? We must have a 0 in the most significant place. So that means there's only 4 possible numbers, 2 to the 2 minus 1. And that's the same as before, 0, 0, 0, 1, 1, 0, 1, 1. Good. So that's obviously 3, 2 plus 1, that's 2, that's 1, that's 0. Good. Now, I want the negatives of these. Now, there's this thing with 0 we're going to have to sort out. You remember in the previous one with the signed representation, we got this 2 different representations of 0. We'll come back to that in a minute. How do I get the negative number of a positive number? I complement the number, flip the bits, I add 1, and that will give me the negative representation of that positive number. So let's just go ahead and do it for all of these, and we'll also see what happens to that 0 right there. Okay, so let's just start with 1, and I'll come back to the 0 in a minute. So please, if you will, complement 0, 0, 1. That's 1, 1, 0. Add 1 to that. So you can do this in good old-fashioned what you learned in grade school. You put a 1 under here, you add those 2, you add these 2, you add these 2, remembering to carry and doing a 1-bit addition, binary addition rather. So that 0 plus 1 is 1, and then there's nothing to carry. So 1, 1, 0, the complement of this plus 1 is this. That is negative 1. That's it. That's the representation. Okay. Let's do this one. Let's flip the bits. 0, 1, 0 gives me 1, 0, 1. 0 goes to 1, 1 goes to 0. Add 1, please. Okay, what's 1 plus 1? 2. What's 2 in binary? 1, 0. So the 1 carries into this position and the 0 comes down. Then 1 plus 0 is 1, and then I've got a 1. So I've got 1, 1, 0. That is negative 2. Okay? And notice again that this position here must always be a 1 because when I flip the bits, I'm always going to have that 0 flip into a 1. Let's do one more. Flip 3, which is 0, 1, 1. It goes to 1, 0, 0. Add 1. That, of course, is just 1, 0, 1. That is negative 3. Okay? Now let's see what happens with 0. You can sort of see what's going to happen, by the way. So what happens when I complement 0, 0, 0? I get 1, 1, 1. And what happens when I add 1 to this? Well, okay, so let's put the 1 here. I'm going to carry the 1 and drop the 0. That's 2 again. I'm going to carry the 1, drop the 0. That's 2 again. I'm going to carry the 1 and drop the 0. So I've got all zeros, and then there's this 1, which we call an overflow. It's the 4th bit. But I've only got a 3-bit number. That 4th bit, it goes away. We can't represent that. And so I end up with, very nice, 0. So this is one very nice thing about 2's complement is that the 2's complement of 0 is 0. Now, one of the strange things about 2's complement is these numbers are a little cryptic, right? If I just give you this number, it's not immediately obvious that's -2, -1, or -3. You have to sort of reverse the process to get back, okay? But I'm going to show you that for a computer, this representation is fantastic because it makes things like arithmetic very easy. And by the way, we only have 1 0, which is just a nice thing to have. Okay. So one odd thing here is we seem to have lost a number. Why? I've got 0, 1, 2, 3, and I've got 0, which is the same 0, and then I've got -1, -2, -3. So I only have 7 numbers. But with 3 bits, if this was an unsigned binary numbers, how many numbers should I have with 3 bits? 2 to the 3 minus 1, I should have 7 numbers, right? From 0 to 7. I've only got 1, 2, 3, 4, 5, 6, 7. Where did that last number go? Huh. Well, something's missing, yeah? So where is it? Let's see. Well, okay. I see that I have 4 numbers starting with a 0, but I see that I only have 3 numbers starting with a 1. So which one is missing? Can you see it? Good. 1, 0, 0. It's not in here. Okay. Now, what does 1, 0, 0 correspond to? Well, it's this sort of weird 2's complement number. I don't know. But I do know this. I know it's a negative number. So how do I figure out what the positive correlate is? Well, I've got to run this process in reverse. So what do? I have to subtract a 1 from here, complement again, and then I get the positive number. And by the way, why do I complement again? How is that the inverse? Well, if I go from 0 to 1 by flipping, I can go from 1 to 0 by flipping again. So if you complement a number twice, you get back to it. So the inverse of complementing is just complementing. All right, so let's figure out what this is. What is this number? I mean, you sort of know it's probably -4, but let's convince ourselves of it. All right, so let's do 1, 0, 0. We're going to subtract 1, we're going to complement, and let's see what we get. All right, what's 1, 0, 0 minus 1? Okay, so a couple of ways you can do this. Here's one. You can just write out the binary numbers in order. There's 1, 0, 0, and you can subtract 1 by seeing that the previous number is just 0, 1, 1. Okay, good. So 1, 0, 0 minus 1 is 0, 1, 1. Let's complement the bits. So that's going to give me 1, 0, 0. What is that? 1, 0, 0. So this is now the positive number. Notice, by the way, there's a 1 there, which looks weird because there should be, by definition, a 0. But this is not. This is the negative number. We're simply reversing it. So this is 2 to the 0, 2 to the 1, 2 to the 2. That's 4 here, which must mean that it's -4 over here. All right, good. So now what we have is an interesting asymmetry. If I had an n-bit unsigned binary numbers, I would be able to go from 0 to 2 to the n minus 1. So I'd have 2 to the n total numbers, but the max number would be 2 to the n minus 1. With a n-bit signed using 2's complement binary number, I go from -2 to the n minus 1 to 2 to the n minus 1 minus 1. That is, there's one less positive number than negative number. Let's make sure this makes sense to us, yeah? So in this case, what do I have? N is 3, right? So if I have n is 3, then what is this representation? So it's 2 to the 3 minus 1, which is 2. 2 to the 2 is 4, so that's my -4. Here I've got 4 minus 1, so that's 3 right there. So there's a slight asymmetry. And by the way, why is there an asymmetry? Just because there's only 1 0 now, right? So you're going to have one more on one side than the other, and it just turns out you have one more negative number. It turns out in practice this doesn't matter at all, but just notice the slight asymmetry here. Okay, so why? I mean, this just seems like an awful lot of work and awful lot of hassle to do this 2's complement, because now I can't read these 2's complement numbers trivially. I've got to go through subtracting 1 and complementing it. So why am I doing this? Well, one reason is you get the single 0 representation, and that's nice. But here's the real reason, is that when you do arithmetic with 2's complement, it works out beautifully, and let me show you how that works. All right, so let's go back to unsigned binary numbers, and let's just do some binary arithmetic. So let's say I want to add 2 plus 2. That's, of course, in base 10. Let's write out the 4-bit binary representation of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So 2 is just 1 times 2 to the 1, and then 0 everywhere else. So there's 2, there's 2. All right, how do I add? Same way I add in base 10. So just column by column. 0 plus 0 is 0. 1 plus 1 is 2. 2 in binary is 1. I carry the 1, and I drop the 0. So now I've got 1 plus 0 plus 0. That's 1. And then I've got 0. So that is the 4-bit sum of these two 4-bit numbers. And of course, what is this? Well, that's 2 to the 0, 2 to the 1, 2 to the 2. That's 4, and that's of course 4. So in the same way that I can add in base 10, I can add in base 2. You just add up, but you just do everything in base 2. So let's see how this works if we use the old-fashioned signed representation, the non-2's complement. Okay. So let's sum up 2 and negative 2. Of course, that should be 0. Well, in the old-fashioned signed representation, 2 is what? 0, 0, 1, 0. That 0 tells me it's positive, and then I get the 3 bits to represent every number between 0 and 2 to the n minus 1, which in this case is 7. Now, to make this negative, I simply flip that bit to 1, and everything stays the same. I love this representation. I find it really easy to read. I don't have to go through all this sort of computation to go from 2's complement back to regular binary so I can figure it out. But let's see what happens when we try to add these two things up. Okay, 0 plus 0 is 0. 1 plus 1 is what? 2. What's 2? Carry the 1, drop the 0. So now I've got 1 plus 0 is 1. And then I've got 0 plus 1 is 1. And that's what I get. Is that 0? Absolutely not. So the simple, and by the way, this makes sense. It shouldn't be 0 because these aren't numbers in the same way. They represent sign. So this makes no sense at all. And so doing that simple arithmetic with signed numbers simply doesn't work. And by the way, that's not an accident. Take any two positive, negative numbers, try to add them up, and you won't get 0. So here's 3, here's negative 3, sum them up, you get this mess here, which of course is not 0. But when you do this with 2's complement, it's really nice how this works out. So let's find out. All right, so let's add 2 and negative 2. Now here's the drawback. What is negative 2 and 2's complement? Well, I got to do the calculation. Okay, fine, let's do the calculation. So negative 2 is I complement this number and add 1. So please complement for me 0, 0, 1, 0. That's up here. Those zeros turn into ones, the ones turns into zeros, and then I add 1 and I get that number right there. Okay, good. So that in 2's complement is negative 2. Let's drop that down, and now let's add the old-fashioned way. All right, 0 plus 0 is 0. 1 plus 1 is 2. Carry the 1, drop the 0. 1 plus 1 is 2. Carry the 1, drop the 0. 1 plus 1 is 2. Carry the 1 last time, drop the 0. That 1, by the way, is an overflow. It's the 5th bit. It's get flushed, don't care about it. And now I've got 0. So notice this very beautiful representation allowed me to do simple bit addition, which, by the way, is where all the magic is in computers doing those types of computations, and it's incredibly simple. Let's do another example to show you that's not a fluke. So in 2's complement, 4-bit 2's complement, this is still a 3. 2 to the 0, 1. 2 to the 1, that's 2, so 2 plus 1 is 3. So that's 3, and then, of course, that number has to be a 0 if it's a positive number. Let's figure out what negative 3 is, all right? Go back up here, complement, the zeros turns into 1s, the 1s turn into 0. Add 1, I go from 1, 1, 0, 0 to 1, 1, 0, 1. That right there is negative 3. Drop it down, add up. All right, 1 plus 1 is 2. Carry the 1, drop the 0. 1 plus 1 plus 0 is 2. Carry the 1, drop the 0. 1 plus 0 plus 1 is 2. Carry the 1, drop the 0. Last one, 1 plus 0 plus 1 is 2. Carry the 1, that's an overflow, it's our 5th bit. Drop the 0, and you get 0. So when you add 2 n-bit 2's complement binary numbers, simple binary arithmetic just works. And that is really beautiful. And by the way, not at all obvious when we set out to do this. It seemed like we were doing this weird thing in this representation that's hard for us to read. But it turns out it's incredibly nice for the computers because it allows computation to happen very nicely. Okay, this is great. we now have positive numbers and negative numbers. We need a little bit more, and then we're going to start looking at the nature of computation on binary numbers. All right, we'll see you in a few minutes.